Now, in the past few videos, I've been working with formulas and symbols quite a lot, and obtaining expressions for power, RMS voltage, and the mean power. Now, in this video, I'm going to use these formulas that I obtained to do a simple calculation using something that we are familiar with, which is our mains power supply, our mains voltage in a house, and the light bulb that gives us lights at night. So let me start by using the example of, say, a mains power supply that is 240 volts. Take a long time to clear. It's the average power. Now, okay, what else do I need? I would need, okay, let me write out the formulas that I need here. Okay, I'm going to need, right, I wouldn't use this value for R, so I'll clear that too. Now right. I would need power is equal to maybe VI and V squared over R. I might need V equals to IR, Ohm's law. Would need this formula for alternating currents. Let's see. I would need the formula for RMS voltage, right? Okay. It's peak voltage over root 2. I would need the expression formula for average power. Average power is equal to half of the peak power. Probably need this. Okay, that should be fine. Right, so I'm going to take some example values that I'm going to use. Let's see. Okay, so I wouldn't use 1.5 volts. I'm going to assume a mains voltage, that this is a mains voltage of 240 volts. So that's not used in all countries. So for example, we would have, say, 240 volts or so in the UK or in Singapore. Now, and suppose that this mains power supply in our house is connected to a light bulb. Now let's say this is a cheap filament lamp that we might buy from the supermarkets that has a rating. It's a rating of 240 volts and 60 watts. So not too bright, just a medium brightness. Right, what I'd like to do is to calculate some of these values, right, based on this rating, so that we can be more familiar with what really goes on in our mains power supply and also be more familiar with these formulae. Okay, so the numbers here are the rating. As I mentioned many videos ago, doesn't mean that the voltage connected to the light bulb must definitely be 240 volts. Yeah, you can connect any voltage to it, or you can even not connect anything. But the rating here just means that if you connect a 240 volt power supply voltage to the light bulb, then the power given out by the light bulb in light and heat would be 60 watts. Right, we need one more detail, and that is the frequency of the mains power supply. Now that's usually 50 Hertz or so. About 50 Hertz. So I'm just going to take 50. So I'm just going to start by calculating various numbers that are related to this, just to get some practice. Okay. Now let's start with this 240 volts. Now the 240 volts that we are familiar with when we use mains electricity. These 240 volts that we normally hear, that are normally written, say on the rating for the light bulb and so on, it is actually not the peak voltage. It is not the V0 in this formula. So that's the first thing we must understand about the mains voltage when we learn about alternating current. This 240 volts is the RMS. It's actually the RMS. Okay, so let me write this down here again just to be very clear. It's the RMS voltage. Okay, and knowing this makes a big difference, because the RMS is actually quite a bit smaller than the actual peak voltage. So let me start by calculating the peak voltage of the mains if it's 240 volt RMS. Now I'll start by rearranging this to make V0 the subject. V0, the peak voltage, would be root 2 times VRMS. Now root 2 is about 1.4 something, okay, and VRMS in this case is 1.41 something, okay. And VRMS in this example is 240 volts. So using our calculator, we will find that the answer is, okay, I'll just take an approximate value. It's about 340 volts. And that obviously is a lot bigger than 240 volts, right? It's 100 volts bigger. So that's the actual peak voltage in the mains power supply. Okay, so it's good to be aware of this when we learn about alternating currents. Now the other thing is about the frequency. From the frequency we can find a period. We find a period by taking 1 over the frequency. So 50 Hertz means 50 cycles per second. So therefore the time for one cycle is 1 over 50, which is 0.02 of a second. Oh no, wait, that's wrong. It's 0.002 of a second. Okay. Okay, so far so good. What else can we find? Right, we can find the power. So since 240 volts is the RMS voltage, what about the 60 watt? Is it the peak power or the mean power? Well, I would think that if we don't know any better, that the mean is a more likely answer. For the simple reason that the actual power fluctuates. The actual power keeps changing. It goes up and down as we have seen. So quoting the peak voltage might give the wrong impression that the power is always that big. So in fact, that's the case. The 60 watts here is really the average power. Okay. So let me write this down. The average power, P with a line on top, that's how I write it, is the 60 watts. So since we have this formula, we can then find the peak power. Peak power is therefore 2 times the mean power, which is 2 times 60, and that would be 120 watts. Okay, so now that we have these numbers, let me sketch a graph. Okay, let me sketch a graph of each of this. Let's say the voltage. For the voltage, V. I'm going to sketch a graph of the voltage against time. The period is 0.002 seconds. Voltage is in volts, and the peak voltage is 340 volts. So it would look like this. The graph would look like this, and the peak voltage write the peak value here is 340. Okay, so that's what a graph of our mains power supply might look like. And for the power, the actual power that would happen in the filament lamp, okay, so it would look like this. Power in watts. So it would go up and down following a sine squared graph as we've seen in the past videos. And the peak power would be 120 watts. So that would be the power actually happening in this light bulb. And it's interesting to think about the effect this has on the light bulb. I mean, we might imagine that since the power and the voltage is sort of keeps going back to zero repeatedly, you know, like the power, it goes up, come back to zero, go up, come back to zero. So wouldn't the light bulb keep getting brighter and darker and brighter and darker? Well, kind of a little bit, but we wouldn't notice it because of the very short period. You see that the cycle is 1/50. Okay, so this from here to here is 0.002 seconds. So from here to here, or from bright to dark to bright, okay, this distance is just 0.001. 1 millisecond. So the time it takes to be bright and dark happens in just 1 millisecond. Now, if you have ever looked at if you look at the light bulb when you switch off the light, right? Let's say your filament lamp and you switch off the light. If you look at the light bulb when you switch off the light, you'll notice that the light bulb does not just go dark immediately when you press the switch. It will sort of dim, right? It might just go dark in half a second or a second, right? But you can actually see it getting dimmer and then it goes dark. And that sort of time scale is maybe of the order of half to 1 second, at least. So, and here we are talking about a power that keeps basically switching on and off, every 1 millisecond. So every time it switches off, and the bulb will start going dim. All right, but it's going to take 1 second to do that. But in 1 millisecond, right, 1 millisecond is like 1 over 1,000 of a second. So in that extremely short time, the power has come on again. So the light bulb will go bright again. So before the light bulb has any time to go dark, the power comes back on. So we'll never notice it. Right? Perhaps if it's some very accurate instrument, we can measure the light bulb flickering a little bit at this sort of time scale.